Quantum mechanics describes the microscopic world with unmatched precision, allowing us to predict the behavior of atoms and subatomic particles with astonishing accuracy. Yet, its picture of reality is famously bizarre, challenging our everyday intuitions about how the universe should work. Particles act like waves, existing in multiple possibilities at once until observed, a concept that has puzzled and fascinated physicists for decades, raising deep questions about the nature of existence itself. Enter Bohmian mechanics, also known as the de Broglie-Bohm pilot wave theory, a bold and intriguing attempt to make quantum physics less mysterious and more intuitive. In the 1920s, Louis de Broglie first proposed that particles are guided by real, physical waves, suggesting a hidden order beneath quantum randomness. However, his idea was overshadowed by the probabilistic Copenhagen interpretation, which became the mainstream view and dominated scientific thinking for decades. In the 1950s, David Bohm revived and refined this concept, offering a universe made of definite particles steered by an invisible quantum wave, restoring a sense of underlying reality. In Bohm's view, the universe is fundamentally deterministic. If you knew every particle's position and the guiding wave, you could, in principle, predict the future exactly, leaving nothing to chance. The apparent randomness of quantum mechanics, Bohm argued, is just an illusion born from our ignorance of these hidden details, suggesting that reality might be far more orderly than it seems. To grasp Bohmian mechanics, we must first face quantum theory's biggest puzzle, the measurement problem. Standard quantum mechanics says particles exist in a superposition, spread out like a cloud, until measured, when the wave function collapses to a single outcome. This collapse is sudden, unpredictable, and deeply mysterious. What counts as a measurement? Why does it cause collapse? The theory doesn't say. It draws an arbitrary line between the quantum world of possibilities and the classical world of definite outcomes. This duality troubled Einstein, who disliked the idea of randomness at nature's core. Many physicists find this unsatisfying, suspecting there's a deeper reality behind the curtain. Bohmian mechanics sidesteps the measurement problem by eliminating collapse altogether, offering a radically different perspective on quantum reality. Here, the wave function evolves smoothly and continuously, always guiding a real, tangible particle with a definite position. No magic, no sudden jumps or mysterious disappearances. Measurement is just another physical interaction. Nothing special happens. The pilot wave steers the particle to a specific spot, matching quantum predictions but following a continuous deterministic path that never breaks stride. In the famous double-slit experiment, the particle itself goes through one slit, while its ghostly pilot wave passes through both, creating an interference pattern that ultimately guides the particle's landing on the screen. The mystery of self-interference vanishes. It's the wave, not the particle, that interferes with itself, shaping the outcome in a way that seems strange but is entirely logical in this view. Observers play no special role. The universe unfolds by the same rules, whether we watch or not, with or without conscious minds to witness it. The apparent randomness we see is just our ignorance of the particle's starting point. If we knew everything, the outcome would seem inevitable. In Bohm's universe, the outcome is set from the very beginning. The dice were cast at the Big Bang, and everything since has followed a hidden but determined path. Bohmian mechanics stands out for its realism. Particles are real, with definite properties, even when unobserved. Unlike the standard quantum view, where reality seems to blur until measured, Bohm's approach insists that the world is always concrete, whether or not we're looking. This dissolves many quantum paradoxes that have puzzled scientists for decades, offering a more intuitive way to understand the quantum world. Take Schrödinger's cat. According to Bohm, the cat is always either alive or dead, never both at once. There's no mysterious in-between state. The theory erases the fuzzy boundary between quantum and classical worlds. Everything is quantum at its core, but large objects behave classically because their pilot waves average out, smoothing over quantum weirdness. There's no magical collapse of the wave function, just a seamless, natural transition from quantum to classical behavior as systems grow larger and more complex. This is the kind of complete objective reality Einstein sought. A universe that exists independently of our observations, governed by clear rules. Bohmian mechanics suggests quantum strangeness is a reflection of our ignorance, not of reality itself. The uncertainty comes from what we don't know, not from nature being fundamentally uncertain. The wave function is only half the story. The other half is the real positions of particles, guided by the wave like a hidden hand shaping their paths. Bohm dared to describe a quantum world with its feet on the ground, offering a vision where reality is always present, waiting to be discovered. Bohmian mechanics restores realism, but at a cost, non-locality. In Bohm's universe, events can influence each other instantly, no matter the distance, a feature Einstein called spooky action at a distance. Consider two entangled particles, measure one, and the pilot wave instantly alters the other's path, even light years away. This isn't just knowledge, it's a real, faster-than-light influence. The standard view is local until measurement. Bohm's is non-local always. Bohmian mechanics sacrifices locality to preserve determinism and realism. You can have definite properties or strict locality, but not both. Bohm chose a universe where everything is connected in ways that defy classical intuition. Bohmian mechanics faces major practical and theoretical challenges. For many particles, the pilot wave exists in a high-dimensional configuration space, not in our familiar 3 dimensions. This makes the guiding wave seem abstract, undermining its intuitive appeal for many physicists. The theory also struggles with relativity. Its non-locality clashes with Einstein's speed limit. Attempts to create a Bohmian quantum field theory have been complex and incomplete. Bohmian mechanics says little about gravity or quantum gravity, leaving it sidelined in modern physics. It offers clarity for simple quantum systems, but falters as physics advances further. The deepest criticism of Bohmian mechanics is its lack of symmetry. Quantum mechanics allows multiple, equivalent mathematical perspectives. Bohmian mechanics works only in one. This breaks the elegant symmetry at the heart of quantum theory, making Bohm's approach seem incomplete. As Feynman said, nobody understands quantum mechanics, not because we can't use it, but because its reality is so alien. Bohmian mechanics offers a compelling ghost story. Real particles, deterministic laws, and a non-local pilot wave. Yet its practical difficulties and broken symmetries suggest it's not the final answer. The quantum world remains stranger than we can imagine, and the true story may be one